Hi, in this video we'll have more examples on conservation of momentum. A problem here, two ice skaters, Danielle of mass 65 kilograms and Rebecca of mass 45 kilograms are practicing. Danielle stops to tie his shoelace and while at rest, is struck by Rebecca, who is moving at 13 meters per second before she collides with him. After the collision, Rebecca has a velocity of magnitude 8 meters per second at an angle 53.1 from her initial direction. Both skaters move on the frictionless horizontal surface of the rink. What are the magnitude and direction of Daniel's velocity after collision? So for this case, we need to figure out where the particles are going. So here, one, we'll have to write before collision. So here you'll have before collision. So if you'll notice, Daniel stops to tie his shoelace, so that means to say that he is at rest. So for this case, we'll have to draw some x, y coordinate in order to locate those two things. Okay, next is that here at the origin, here's the location of Daniel. Next is that if you'll notice, Rebecca is moving 13 meters per second, so most likely it's positive, so it would only mean that Rebecca is on this portion here. And he's moving 13 meters per second. Meters per second. So here, next is that we'll draw the situation after collision. The two particles collide at this point here. So Rebecca has a velocity of 8 meters per second at an angle 53.1 from her initial direction. So you'll measure 53.1 from here. So you'll have 53.1 degrees from her initial direction. And then the location of Rebecca is simply here in the first quadrant, and its velocity is simply 8 meters per second. Okay, so here it's asking for the magnitude and direction of Daniel's velocity after collision. So we don't really know where Daniel is. We don't know if he's moving along positive x direction here or if he's moving here along the fourth or first quadrant. So the final answers would tell us on what quadrant. So we'll assume that Daniel is moving here. Okay, so next is that we're gonna place some labels and take note of the given formulas. So here, we'll call Rebecca as mass 1. So here for the given, we'll have mass 1, which is simply equal to 45 kilograms. So you'll have here 45 kilograms. And we'll call Daniel as mass 2, which is simply equal to 65 kilograms. So here, if you'll notice, is that by using the conservation of momentum, take note momentum is conserved in any type of collisions. So if you'll notice also, this is a two-dimensional collision. So momentum is a vector quantity. So you cannot just simply add the vectors. You'll need to consider its directions too. So here is that before collision, we're going to note all the velocities of each of the particles. If you'll notice, V1 has a magnitude of 13 meters per second. But then you'll have to take note to look for its v1x and v1y. Okay, so if you'll notice, it's moving along positive x direction. Okay, here's the positive x and then the positive y. So that would only mean that its v1x is equal to 13 meters per second. And its y component, there's none, so that would be 0. Next, for your v2, its magnitude is 0, right? Since it's at rest. So both v2x and v2y are simply equal to 0. So you'll need to find the components for each of the vectors. That's before collision. And then after collision, here, this is Rebecca, so that would be your mass 1. So we'll call this one as v1 prime. And what we are looking for is the magnitude and direction of your v2 hubs, v2 prime. v2 prime. Okay, so here, after collision, so we'll have here your v1 prime is its magnitude is simply equal to 8 meters per second. But then its components, if you try to look at its components, yes, it has x and y components since it's lying along the first quadrant. So here, we'll have to put some arbitrary x and y axis here. So if you'll notice, again, it's lying along the first quadrant. And along this way is positive y, here positive x. If this is 53.1, well, here this is also equal to 53.1 degrees. So using component methods, so here, this will be your v1x prime, and this one here will be your v1y prime. So your v1x is on the adjacent side of 53.1, so that would only mean cosine. So that means to say this vector is towards right, so that means to say positive, so you'll have here v1 prime cosine 53.1. So the magnitude is 8, so you'll have 8 cosine 53.1 degrees I hat. So you'll have here the answer will be 4.80 meters per second I hat. Next, your v1y prime is on the opposite side of angle 53. So that means to say sine. So you'll have v1y sine 53.1 degrees. So again, I repeat, it's positive, it's moving along or towards positive y-axis. So you'll have 8 meters per second, the magnitude of v1 prime, and then you'll have sine 53.1 degrees j hat. So the answer will be 6.40 meters per second j hat. So if you'll notice, there are 4 components, all in all, 1, 2, 3, 4. So the next step is to use conservation of momentum. So again, I repeat, using the conservation of momentum equation. So you'll have M1. So I forgot, you need to use components too. So you'll have here the x component. Okay, so you'll have M1 V1x plus M2 V2x is equal to M1 V1 prime x plus M2 V2 x prime. So next is that you're going to substitute your v1x has a value of 13, so meaning to say you'll have m1 v1x. Your v2x is simply equal to 0. And you're looking for the variable v2x prime, right? So you're looking for this variable here. So all you have to do is to subtract m1 v1x prime both sides of the equation. So you'll have m1 v1x prime, which is simply equal to m2 v2x prime. Next is to what? Divide both sides by m2. So you'll have m2, m2. So cancel this one out. So you'll have your v2x prime is simply equal to, we're gonna factor out this m1 here. So you'll have v1x minus v1x prime over m2. So you'll have here m1, which is 45 kilograms, times your v1x is equal to 13 meters per second, minus the v1x prime is 4.8. So you'll have, I forgot also to put some unit vectors here. I hat, j hat, I hat, j hat. So you'll have 4.80 meters per second I hat all over its mass to 65 kilograms. So there are some units that cancels out here, and meters per second can be factored out from the parentheses. So your v2x prime is simply equal to 5.70 meters per second. And it's moving along positive x-axis. Okay. And it's moving along positive x-axis. Next is we're going to solve for the y component, the v2y prime. Okay, so again, I repeat, for this case, our v2y prime, we need to look for your v2y prime, v2x prime, and v2y prime. Okay, what are the values of these three? So we actually have solved the v2x prime. We've just solved the v2x prime, which is equal to 5.7. So here next, in the y component, as a continuation, in the y component, so you'll have here, you'll use the same equation here, but you'll have to replace x with y. So you'll have here m m1 v1y plus m2 v2y is equal to m1 v1y prime plus m2 v2y prime. So take note that this is before collision. Again, I repeat, before collision. And these two here are after collision. So here, m1 v1y and m2 v2y before collision, if you look at these components here, both of them are 0. So that means to say the left side of the equation is simply equal to 0. And we're looking for this variable here. So all we have to do is subtract m1 v1 prime both sides of the equation. So you'll have here negative m1 v1 y prime is equal to m2 v2 y prime. Divide both sides by m2, so you'll have your v2y prime is simply equal to negative 45 kilograms multiplied by 6.40 meters per second all over mass 2, which is simply 65 kilograms. So this units here cancels out. So take note that we'll have units of j hat here. I forgot to write. So your v2y prime is simply equal to negative 4.43 meters per second j hat, or can be written as 4.43 meters per second negative j hat. Okay, so if you'll notice, its y component is negative. So you'll have an idea where v2 prime is lying. So its x component is positive and its y component is negative. So that would only mean that it's lying along the fourth quadrant. So next is that we'll have to look for the magnitude of the v2 prime. Okay, here. We already have a value for this too. We have 5.70, right? Meters per second, and this is negative 4.43 meters per second. Okay, so here, so solving for the magnitude of V2, so we have V2 prime rather. So you'll have here, we'll have to draw first. We have to confirm first, where is it lying? Or on what quadrant is it lying? So here your V2 x prime is positive, so we'll assume that this points towards positive x direction, while the other one points towards negative, I mean rather positive y direction. So your v2 x prime is positive, so you'll have v2 x prime. And your v2 y prime is negative, so you'll have here downward, so you'll have v2 y prime. So what we're looking for is its magnitude. Okay, it's crooked. So we're looking for its magnitude. So this would be v2 prime. So in looking for the magnitude of these vectors, we're going to use Pythagorean theorem. So v2 prime, magnitude of that one, is simply equal to the square root of v2 x prime squared plus v2 y prime squared. So you'll have square root of 5.70 meters per second squared plus negative 4.43 meters per second quantity squared. And the answer will be 7.22 meters per second. That would be the magnitude of your V2 prime. Next is that we're going to look for its direction. Okay, again. Next is we're going to look for its direction. So we're going to use trigonometric functions. So P2 prime. So we're going to use tangent function for this case, wherein tangent theta is equal to opposite over adjacent. So your theta is simply equal to tan inverse. The opposite side is your V2 y prime, which is negative 4.43 meters per second over the adjacent side of angle, shall we say theta, is simply v2x prime, so you'll have meters per second. So the answer would be 39 degrees. It's from east going south, so that means to say that would be south of east. So the final answer will be for letter A is that your V2 prime, its magnitude and direction, its magnitude is simply 7.22 meters per second, and its direction is 39 degrees south of east. Okay, take note that Daniel is located on the fourth quadrant with the direction of 39 degrees and a magnitude of 7.22 meters per second. So for letter B, what is the change in the total kinetic energy of the two skaters as a result of the collision? So when we say change, we need to say delta of the total kinetic energy. So again, when we say change, it's asking for its final kinetic energy minus the initial kinetic energy of the system. For letter B, it's asking for the total change of the kinetic energy. So you'll have here change, meaning to say final kinetic energy minus the initial kinetic energy of the system. So here, we'll try to find for the kinetic energy, total kinetic energy of the system. So you'll have before collision. So here we'll have K initial, total kinetic energy before collision is simply equal to 1 half m1 v1 squared plus 1 half m2 v2 squared. So we already know that the mass 2 before collision, Daniel, which is Daniel, is at rest, so its kinetic energy is simply equal to 0. So we are left with the kinetic energy of Rebecca, which is 1 half times 45 kilograms times her initial speed of 13 meters per second squared. So the initial kinetic energy of the whole system is equal to 3,802 joules of kinetic energy. Next is we're going to solve the final total kinetic energy. So that would be after collision. So we'll have KE final is equal to 1 half m1 v1 prime squared plus 1 half m2 v2 prime squared. So we're going to factor out the 1 half. So you'll have here m1 45 meters per second times 8, the magnitude of v1 prime meters per second squared, quantity squared, plus quantity 65 kilograms times 7.22 meters per second squared. So the answer would be 3,134 joules of energy. Final. Okay, so from 38 to 31, so all we have to do is to find the change. So we'll have here delta K E is equal to K E final minus the kinetic energy initial. So we'll have here final 3134 joules minus 3802 joules. So the change of the kinetic energy of the whole system total is simply equal to negative 668 joules.